Good evening, sir. Today I'm going to present both theses combined, as you said previously in last week, that make PPT of both combined thesis. So I have made this PPT. The first thesis name is a microwave radiometer for internal body temperature measurement. Uh, in this thesis, the measurement of physical temperature using a microwave radiometer receiver. The common application of microwave radiometer are radiometer astronomy, atmospheric sensing and earth sensing, and some industrial process such as cement and brick manufacturing. As you can see in this figure, radiometer receiving blackbody radiation in a form of propagating electromagnetic wave from an object with brightness temperature, that is TB. This is proportional to physical temperature time, the emissivity. The power received by antenna is proportional to brightness temperature. Uh, Same as microwave radiometer for non-invasive temperature measurement is based on near field power perception and hold promise to achieve the partial resolution and seeing and sensing depth necessary for variety of medical application including cancer detection, monitoring drugs delivery for cancer treatment, hyperthermia, temperature control, hypothermic neural rescue of infant suffering from hypoxia and detection of vascular reflex in a child. Also utilize non-invasive near-field radiometric measurement. The concept of radiometry is a device. The radiometer is a device that measures incoherent radiation. Matter emits electromagnetic energy based on its temperature in all direction with spectral brightness described by Planck blackbody radiation law. The H is Planck constant 6.63 into 10 raised to minus 34 J seconds. C is the constant of light in vacuum per seconds. K is the Boltzmann constant 1.38 into 10 raised to 23 J, and T is the temperature in Kelvin. Now you can see in this figure that shows the spectral brightness was frequency from temperature ranging from cosmic microwave background 3K to temperature sum of 6000 K. The term brightness of microwave terminology differs from the optic terminology, which is radiance. However, in this work the term brightness will be used. Now, in this figure, it is the power delivered uh, by an antenna placed inside a black body and close to temperature T equal to off. And in B section, in this a resistor R, a resistor maintain a same temperature. In this, a lossless antenna is placed in an enclosed with observer that is kept at a constant temperature T as shown in figure, and substituting the Rayleigh Jeans law from 1.2 into 1.5, noting that the lossless antenna. In the second figure, match resistant maintain a temperature T. As seen in figure, the power received by the antenna is the same as received by the match resistor. Emitted. To this point, only black body have been considered as the ideal emitter and observer of radiation. In reality, objects are gray bodies. A gray body will emitter or a observer less than that of perfect black body. Thus, a gray body, the term brightness temperature TB is used as it is the observed temperature of the object which is less than physical temperature. The brightness temperature TB is the brightness temperature of the object and does not include the scattered brightness temperature from the environment. Is essentially a plane wave power transmission coefficient which is illustrated by considering the interface between the homogeneous dielectric free space as shown in this figure 1. This MST and the brightness temperature you can see where the tap 0 is apparent temperature just below the surface of this and funnels coefficient and also tap at funnels are dependent on angle of incidence theta 2 and the polarization as shown in this figure. Uh, Now, what is the near field radiometry for in medical field in medical application? In general, for radio astronomy and atmospheric and earth sensing, the antenna is electrically far from sensing targets such that receive electromagnetic power is in form of propagating plane waves. Medical application detail in overview, the spatial sensitive require balancing sensing depth in the transverse selective. Thus result in the antenna must be a close to target or even in direct contact with the body in case of wearable device. To determine this, the antenna temperature, the most important and necessary to find first to find the proportion of power received by the antenna and then from the different differential volume relative total received thermal power for an abbreviate stack of homogeneous complex primitive materials such as human tissues. Now you can see in this figure the dissipation of the weight function where it is necessary to determine the contribution from a differential volume V this at the temperature T to the overall antenna temperature. Electrical properties of tissue. The weighting function were dependent on dielectric properties of the material close to the antenna, which for medical application are human tissues. The dielectric properties of tissues have widely studied at the standard resource is a series of article as Cablin and C Cablin that include a literature survey measurement and models of various human tissues. For dielectric properties of various tissues in the frequency range is from 10 Hz to 100 gigahertz. An internet resource for calculation of dielectric properties of body tissues from Italian National Research Council is great resource. This is like some kind of analysis which has a problem that required knowledge of dielectric constant is necessary and the simple model to predict frequency depend complexity with the single relaxation that model the dipole polarization will not happen as fast as ionic and electronic polarization taking some relaxation time to reach the steady state. The response of polarization to step electric field. As you can see in this figure, the response of a dielectric material to step to the electric field. The polarization have initial nearly instance response that P infinity. P infinity, the polarization will then reach steady state described as first order process with time constant. Phantom material for medical application. Uh, in This is some kind of uh, details about medical applications and the formula for different diodes model for pure water temperature Celsius source. What is this? As you can see in this table, there is source and double parameters. In 1971, Strang presented expense for the three unknown is diab model as a function of temperature and salinity. The express were compared to measure data from literature at the frequency ranging from 3 to 2.5 gigahertz to 23.7 gigahertz. And in the next it is use its own measure data from 0.0 degrees Celsius to 50 degrees Celsius over the frequency range of 1.1 gigahertz to 57 gigahertz in combination with data from literature, which is valid up to only 100 gigahertz over a temperature range minus 4 to 60 degrees Celsius. And the last which is in which was in 91, presented a model fit to experimental data compiled from literature. This model Debye model is valid only up to 100 gigahertz. Beyond 100 gigahertz or and up to 30 terahertz, double model was used to account both primary and secondary relaxation. Uh, as you can see this have a three signal double model described in the as I described in previous slide were compared over the frequency of 100 gigahertz to 10 gigahertz at temperature 25 degrees Celsius and 1.4 gigahertz over the temperature of 5 degree to 50 degrees Celsius, and the result are summarized in this below diagram. uh, you can see the comparison between of these three models in frequency gigahertz and in temperature Celsius. Complex primitive pure water versus frequency, as I described in previous slide also. From for the first you have the difference between this two figure is the from 100 gigahertz to 100 megahertz to 100 gigahertz at temperature of 25 degrees Celsius 77 degree Fahrenheit and 1.4 gigahertz versus temperature from 5 degree to 50 degrees Celsius. And the next, this is the frequency range interest in between 100 megahertz to 10 gigahertz. The model represented by Lebenthal will be used to determine the dielectric properties of water. As you can see in this figure, the real part of relative dielectric constant and conductive at temperature of 25 degrees Celsius, the real part of relative dielectric constant is relative constant 78.3 to 62.9. However, the conductive changes notably from 0.002 seconds to 16.6 seconds over the frequency of 100 megahertz to 10 gigahertz. What are the design and how proof design from the literature? Uh, the inverse problem of determining the physical temperature of tissues from radiometric observation will like to multiple independent measurement at different frequency or different angles, and multiple frequency are used as a weighting function will be function of frequency, thus resulting an independent measurement. The challenges were there in this using the multiple frequency, as I said in previous point, is the probe must be measuring the same tissues at each frequency, which lead a researcher to develop broadband waveguide apparents that filled with the high dielectric constant to achieve the bandwidth necessary for using a single aperture over 1 to 4 gigahertz, and the application were determined to absolute temperature at the depth is not required. Single frequency may be used. Such single frequency application as detecting a buried hot object with a monopole or determining the body temperature that includes contribution from core body temperature with cavity back slot utilize antenna designed for single frequency, and the comparison between the probes is size, frequency, and application. Multiple discrete frequency with narrow bandwidth less than 5% is used. And what is the different in this work is separate antenna located uh, in close proximity will be used receive thermal power from the same part of the body rather than single antenna matched over the broadband. As I said in previous slide, that that was a comparison between a size, frequency, and application. The you can see in this picture the probe design for literature. This is the application, this is size, uh, and the application is photograph dielectric waveguide, Archimedes spiral, L-shaped monopole, and cavated back slot, and apoplectic antenna. And the frequency of these applications as described in this you can go through this like 1 point for photograph dielectric waveguide is 1 point is ranges from 1 to 3.8 to 400 megahertz band. Wow. And the spiral is ranges from 1 to 3.5, and the L-shaped monopole 1.39 to 1.757, and one and cavity black stall 1.2 to 1.6, and last and the least apical antenna is 3.5. Their dimension and the design for is like 2.1 and 2.8 water, and next as you can see this 3.3 it is in square shape, uh, height and width, and in the L-shaped monopole 2.8, and it is a cavity black slot, so it is 9 into 9 into 2.7 adjustable gap, skin, muscles, and fat, blood, phantom, human tissues, and in the last apical antenna this its dimension is like 5 into 5 into 3.2, human tissue, hand, chest, belly, and hip. Now, now this is the second thesis as discussed. This thesis name is radiometric thermometer for variable tissue, deep tissue monitoring. As as nowadays number of health related application are there ranging from monitoring to diagnostic to therapy which benefit from the knowledge of internal core body temperature. The internal temperature of human body can be considerably different than the temperature of skin. Difference between the core temperature heart and skin varies up to 2 degree Kelvin over the Cardian cycle of healthy person. As you can see in this figure, the skin and the muscle temperature vary in the opposite direction during exercise. While muscle temperature increase with an increase in intensity, the skin temperature decrease due to the sweating, evaporating cooling. There are a number of health related applications. And there are in this there are internal thermometers such as uh, oral, rectal, esophageal, indigestible, uh, which is not so portable, not convenient for long term monitoring, difficult to insert. Indigestible telemetric pills measure temperature which while in the digestive tract for a limited period, and it is not reusable, and their precise position is in the body is unknown. Surgical inserted thermometers are not and non-invasive. As you can see that external thermometer is like such as first of all this example is MRI grant, which grant high partial temperature resolution, and it's expensive, not portable parameter like proton density, diffuse contract, relaxation time, and magnetic transfer ratio, and intermolecular zero quantum coherence, or water proton resonance frequency. Other external thermometer is like CT. CT is what computer tomography, imaging and ultrasound use other temperature sensitive parameters such as CT number and speed of sound. Isothermal tunnel develops below the skin, which makes the subsequent temperature equal to skin temperature where it can be measured non-invasively. Uh, and the microwave thermometry and thermal noise. In this, the electrical noise is a random variable with voltage current mean equal to zero, but with non-zero power, dominate noise from the passive device at non-zero temperature through microwave frequency range in thermal. And as you can see in this figure, and there is an antenna and a terminator transmission line inside a large enclosed. Now I'm going to explain this figure. Uh, this is an antenna and terminator transmission in lying inside a large enclosed. There are three dimensions as you've seen in that figure. Object can be treated as a matched transmission line connected to an antenna inside an iconic chamber at a constant temperature T in thermal equilibrium. Transmission line feed transmission generate thermal noise power which is delivered to antenna, radiate out of chamber. And then meanwhile the antenna receive the noise power from the enclosed and deliver to the transmission line. The true process must be balanced in thermal equilibrium. The noise energy flux incidence on the antenna, and it enclosed in large s ohms with the will be the same of every direction. The free space wave travel at a speed of light c. The noise energy density per unit volume, and the total noise and energy density at the point in summation of contribution from all direction. And now what challenges has been faced to do this is to with designing and manufacturable cost variable wireless radiometer can be categorized to several main regions. The first challenge was designing a microwave radiometer is to detect very low level of black body noise power emitted by the human body. To measure such internal tissues, Temperature at centimeter depth under the skin, lower microwave frequency are used. Forcing operation to tail of black body curve at 1.4 to 1.427 gigahertz. The human body radiate from minus 100 dBm of thermal noise power. And the another challenge is to substitute to interface due to heavy to a very low level of power emitted by the tissues. This can be migrated by multiple stage of filtering in the probe and circuit designed by minimizing of probe and circuit by shielding the radiometer and also by single processing technique. Power variation at the input of radiometer due to zero point 0.1 degree of temperature change in the is less than 0.01 dB and force a high sensitive radiometer designed with translate to very high required system gain which can result in instable. To maintain such a small size power, low power consumption is also important in designing wearable radiometer. And these are other challenges also, and many application relative temperature measurement or monitoring over time or sufficient, while in other cases absolute temperature is required, more difficult to measure and would more likely to require an independent known temperature source from additional calibration during the measurement. Now you can see in this block diagram of variable internal body temperature measurement system. This is in this system. In this, you can see the muscle, fat, and skin. I will explain you this block diagram. Now, the power received from the tissue layer by the narrow broadband probe is coupled to a radiometer which consists of switch that required for calibration a low noise amplifier followed by a band pass filter and a detector circuit. Hot and cold, are used for continuous temperature calibration for radiometer, which is that integrates over a time increases single to noise ratio detector, and the detector output was DC voltage output is digitization process and transmitted through a wireless unit. And the MCU controller unit controls the radiometer switches enabling phases sensitivity detection of the very low human black body power, tissue properties and phantom development. In this, you can see the temperature, there is the tissue, muscle phantom, skin phantom, agar, smoke, salmon. In this, temperature depends and detail frequency depends on the tissue parameter are important for design. Here it is the sphinx to point out the dielectric constant at 1 gigahertz varies from 5.5 fat to 55 muscles, while the conductivity varies from 0.05 s meter second to 0.98 seconds. Uh, um, uh, chicken chicken breast is often used to make the dielectric properties similar to those of human muscles. Chicken breast can spoil after a few days. Salmon is alternative used for some of the measurement. Skin and muscle solid tissue phantom are developed. Uh, these tissues phantom make the electromagnetic properties of real tissues at microwave frequency, and the agusoid solid tissues phantom is also developed in this based on the preparations and all. This is the I got one table in this thesis. This In this table you can see the tissue, primitive and tan and SM. These are the various type of tissues and their primitives and the tanned value and the this value. Now, what was the operating frequency? The first step was designing the microwave radiometer is to choose a operating frequency. As you see, as you can aware that penetrating deep in the skin for a plane wave at IR is about 2 mm. At microwave frequency, electromagnetic wave penetrate through the body tissues such as a few centimeter, enabling the radiometer to track deep tissues temperature variation, working a microwave frequency. At human body temperature, 310 kilo K and radiometer bandwidth of 27 megahertz, 1.8 predict P minus 100 dBm of 15 incident power at the antenna surface. The work is quite frequency and band of 1.4 to 1.427 gigahertz allocated for radio astronomy selected. This frequency band provide a reasonable compromise between a sensing depth of RF interface. Uh, Now I am going to summarize this thesis as in this thesis, microwave radiometer application, existing core body temperature, and available microwave thermometer as overview. Disadvantage and advantage of previously demonstrated method are presented as a motivation to research to this thesis, and various solid liquid tissues phantom are discussed and are required for design and experimental validations. Uh, in this, I have also reviewed the basic theory of black body radiation as a foundation of microwave thermometer and introduction challenges related to the design of microwave thermometer, including frequency choice and sensitivity. And the final device operating was frequency device operating frequency range of 1.4 to 1.4 gigahertz is chosen since it is a quiet band located to radio astronomy is less susceptible to radio frequency interference while providing a few centimeter of sensing. Thank you for the day.